So the atoms of naturally occurring elements are the basic building blocks of Earth's minerals. Most of these elements join with other elements to form chemical compounds. Basically what occurs is that each atom really wants its outer shell filled in order to become a stable compound. When this happens, when they actually get their shell filled, it ends up with the same atom arrangement as the noble gases, which you see in the last column, column number 8, or group number 8, I should say, of the periodic table. So those would be these guys over here: helium, what is this, neon, argon, and krypton. So there are different types of bonding, which we will look at in the coming slides, but it has been found through experimentation that it is electrical forces that hold atoms together and bond them to each other. These electrical attractions lower the total energy of the bonded atoms, and this in turn generally makes them more stable. Again, by typically completing that outer shell of electrons. So, as you can see in the image on that slide, the one I just pointed out too, each red electron is a valence electron of each of the elements. Those electrons on group 1, for example, have one valence electron. So hydrogen, lithium, sodium, potassium all have one valence electron. Those on group 2 have two valence electrons. So those are going to be beryllium, magnesium, and calcium, for example. And so forth and whatnot. So the ones on group 3 will have 3 valence electrons, all of the way till group 8, where they have 8 valence electrons, which is what they are happy with. They're kind of complete. So group 8, or the noble gases as the group is referred to, have very stable electron arrangements with the 8 valence electrons, except helium, which only has 2. And therefore, when they have that filled shell, they tend to lack any chemical reactivity. So for example, because of their lack of chemical reactivity, they tend to be very good tracers for groundwater. So if you trace them from the source to a specific location, then you can sort of have an idea of how old the groundwater is, because they didn't react with any other substance, and so they have been in the water with the same amount pretty much all throughout, which is pretty cool. And I can explain this later on in class if you guys want me to. Okay, so many other atoms belonging to other groups, again, lose or share the electrons all of the time until they end up with an electron arrangement like the one of the noble gases. So this observation that was made led to a chemical guideline, which we call the octet rule. Okay, and this octet rule states that atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. Okay, so octet rules, octet goes after 8, so they want 8 valence electrons on the outside, except for helium, which only has the 2, pretty much. Okay. So although this rule has a few exceptions, it is a pretty good rule of thumb for understanding chemical bonding overall. Okay, so based on the octet rule that we just saw in the last slide, when an atom's outer shell does not contain 8 electrons, it is likely to chemically bond to other atoms to achieve an octet, or an octet on its outer shell. And again, have 8 valence electrons in its outer shell. So a chemical bond itself is going to be a transfer or sharing of electrons that will allow each of the atoms within this reaction to obtain a full valence shell of electrons. Okay? Some of the atoms do this by transferring all of their valence electrons to other atoms so that their inner shell becomes the full valence shell. Does that make sense? So again, for example, let's take sodium, which only has 1 valence electron on its outer shell. Sodium tends to get rid of that valence electron so that the next shell that it has is full, but not gain any more. On the other hand, chlorine, which you have there in the picture, has 7 valence electrons, so it tends to gain one more electron so that its shell is complete. Okay? So that example that I just gave, sodium and chlorine, is a pretty common example, and it's a great way of ionic bonding. Okay, we'll go over this in a second. So sodium basically gives its valence electron on its outer shell and hence become positively charged by giving it away. And chlorine accepts the electron, becoming negatively charged because it just accepted an electron. So electrons are negative. Because it gained one electron, it becomes more negative. Okay, does that make sense? I hope so. Okay, so alone, either of these two elements, chlorine or sodium, are actually deadly upon either consumption or inhalation, basically. But once they have been bonded together, they become salt. That's right. Salt is basically the chemical reaction of sodium and chlorine, NaCl, as some of you know. Salt as a mineral is called halite, and we'll see it in lab. You'll get to taste it and everything, which is pretty entertaining. Salt, as you know, makes food have a stronger taste, and it is key to our system for it to function correctly. So that pretty much comes down to after elements bond, their properties change significantly from being potentially, very dangerous for consumption or inhalation to being completely necessary. Okay, so in the previous slide, we saw the first type of chemical bonding, which was ionic bonding. Again, in that case, one of the atoms it gives one or more of its electrons to the other one for it to gain them. They're going to end up having positive or negative charges in this case. And this is a different type of bonding right here. We have covalent bonding. So this happens when the valence electrons are shared between the atoms. Again, one of the best examples is that one, when two of the hydrogen atoms share their single corresponding electron, and hence sharing both electrons to complete their valence combined shell, if you would. In this case, the bonding does not create ions, so you don't get a negative or positively charged atom. And what holds the two atoms of hydrogen is rather the attraction of opposite charged particles between the protons in the nuclei of either atom and the electrons that are surrounding both of them. So covalent bonds, for the most part, tend to be a little bit weaker than ionic bonds, but not necessarily. It depends on which case you're looking at. So the third type of bonding that we have, which I didn't put in the slides, just so you know, it's metallic bonding. You won't be quizzed on it, but it's still good to know. So metallic bonding occurs when the valence electrons that each atom has are shared among all of the atoms in a substance. So they kind of create a sea of electrons. So it's very similar to covalent bonding in a way, but it is with a large arrangement of atoms. So once they create the sea of electrons, they will bond by the attraction of the nuclei from each of the atoms within this reaction, the attraction between each of the protons in the nuclei of each atom, sharing all of the electrons in this massive sea. Okay, so it's similar to covalent bonding, but with a larger number of atoms. Okay, minerals, as we had said before, are going to be a combination of a set of atoms of specific elements, making up a solid material with a specific chemical formula, an orderly crystalline structure that is inorganic, and that it occurs naturally. Okay, so for example, again, given those specific characteristics of a mineral, ice is actually a mineral because it is solid. It has a specific chemical formula, an orderly crystalline structure. It is inorganic, and it tends to occur naturally. Well, depends. If we put it in the fridge, then not. But if it occurs just by the freezing that occurs by temperature change, then it is a mineral, right? However, again, some of the minerals are made up of one single element, so there is no reaction between, say, hydrogen and oxygen like there is for ice. Some of the minerals, like the ones that you see below, have only one single element that makes up all of the mineral itself. These are called native minerals, okay? So here's a few examples. You have gold, which probably most of you know about. You have diamond right here to the right. You have sulfur down here. That's a picture I took in Yellowstone, and I'll probably talk about it later in the course. You have antimony, you have copper, and then you have carbon. Okay, which in this case is really graphite. Cool. All right, so now we're going to look at the physical properties of minerals. Some mineral samples differ from one another. So for example, one quartz sample may be white and another quartz sample may be pink. Or one may have more impurities than the first sample. However, both of those samples should be equally dense, should break in the same manner, and be equally hard. So we use certain properties in order to help us identify different samples of the same mineral, okay? So that those different properties that make them differ don't confuse us too much and don't make us classify it as a different mineral. So some properties are very distinct to the specific mineral, or very specific, I should say, very characteristic. These properties are called diagnostic properties, and they are things such as a salty taste, which is typical of halite, obviously, or such as being magnetic, which is typical of magnetite and sometimes of hematite, or sometimes effervescing or fizzing with hydrochloric acid, which is typical of calcite. These specific properties tend to be very diagnostic, meaning they only happen with that specific mineral. And so they're very characteristics. Some other properties are more ambiguous and not necessarily specific to one single mineral. So for example, a cleavage of pyroxene may be the same cleavage for plagioclase, but they're completely different minerals. So some properties are not specific to the mineral, and they're called ambiguous properties, okay? So these properties are things such as color, hardness, and we're going to see a few more later. Okay, so the first ambiguous property that we do have in this slide is luster. So luster is an optical property, meaning it can be seen with your eyes, and it's the appearance or quality of light reflected from the surface of a mineral, okay? So there are many types of luster. For example, metallic or submetallic, which means that the light is reflected from the surface of a mineral as if though it looked like a metal, not surprising. Luster can be vitreous or glassy, where some light passes through the surface and through the sample sometimes. Within this property, we have transparent samples, where light passes as well as being basically see-through. So that would be this type. So it is vitreous and it's transparent. But we also have translucent samples that are vitreous. So we have this type right here, where you can see light passing through, but you cannot see an image through the mineral. Does that make sense? So if I were to hold this mineral on the left next to my eye and look through it, I would see light passing through it, and I would probably also see whatever is lying behind it. If I were to hold this other mineral in front of my eye, I would see the light passing through it, but I'd probably see no image of anything that's behind it. Okay, so that's vitreous or glassy. We also have pearly luster, like the one that you're seeing down here, for example. We have dull or earthy luster. So that's kind of something like this that you're seeing on both of these. This is a little bit vitreous if you were to take it smaller samples. We have silky luster, which I don't have an example on that slide, but you'll see in the lab. And we also have greasy luster. I know these all kind of sound like they could be very similar, and that's partly why this is an ambiguous property, right? There's no specific key to them. We need to rely on other properties to identify the mineral, not just on luster.